So now we come to the first rule of thumb, which is called the rule of 10. And this is applicable to volatile chemical exposures. And it is the first part of the checklist tool, the Excel spreadsheet. So each of these rules of thumb are developed from experience of various professional industrial hygienists over the years, but they are also grounded in physical and chemical facts. So the first one is based on the idea of vapor pressure that you're all familiar with. But just to briefly review, the vapor pressure is the pressure exerted by the gaseous phase of a two-phase system, gas liquid or gas solid system. And the pressure of the vapor that is formed above its liquid is called the vapor pressure. So you can imagine there is a pool of some volatile substance, let's say toluene or benzene, and some of these benzene molecules escape from the liquid phase and get into the air above it. And so if you have a closed system, let's say a closed room, a fully sealed room, and on the floor you have a pool of benzene, then the molecules of benzene, some of the molecules of benzene escape into the room air. And the pressure that the benzene molecules exert on the room walls is the vapor pressure of benzene. And if we are in an enclosed space like the sealed room, then this two-phase system, the liquid and vapor system, will arrive at an equilibrium, meaning that at some point you will reach a stage where the rate at which the benzene molecules leave the pool of benzene is equal to the rate at which the benzene molecules leave the air and come back to the liquid phase. And at that point, the pressure exerted by the benzene molecules is called the saturated vapor pressure of benzene, because no more benzene molecules can enter the air because the air has reached its capacity. It is saturated with benzene. And so nature does not allow any more benzene molecules in air at that temperature. But if you increase the temperature of air, then you might get more benzene molecules into the air. But at that temperature, you've reached the maximum and you are saturated with benzene. And the pressure is a fraction of the total pressure, which is equal to 760 millimeters of mercury at sea level. A couple more bullet points here. An agent's vapor pressure at its boiling point, it's 760 millimeters of mercury or atmospheric pressure. And the vapor pressure of specific agents and mixtures is lower than the agent's vapor pressure in its pure state. So, for example, if you have not just a pool of benzene in this sealed room, but actually a mixture of benzene, toluene, and xylene, and a few other things, then the vapor pressure exerted by benzene is, in that scenario, lower than if you just had benzene in the pool. Then the other thing to remember, as I just mentioned, is vapor pressure increases with increase in temperature. And vapor pressures and boiling temperatures are usually reported on the material safety data sheets or MSDS and are available in government sources such as ToxNet or the NIOSH Pocket Guide. And the vapor pressures are usually related to a particular temperature and usually reported at 25 degrees centigrade or 20 degrees centigrade from the standard sources. So in this next slide, we actually get to the rule of 10. What is the rule of 10 as it applies to volatile chemicals? So if you have a volatile chemical such as benzene or toluene or xylene or many of the other volatile compounds, and like we just discussed, if you are in this completely sealed room and you have this pool of this volatile liquid on the floor, then the concentration in the room will be the saturation vapor pressure. But we typically don't have that kind of a situation almost ever, unless you sort of create that in the lab on purpose. But there are many situations that happen in real life work environments that are not completely sealed, but have very poor circulation. The first case is when you have a confined space. So there is virtually no circulation, but there is a little bit of circulation. And so there are any number of confined spaces. For example, you might have a road worker going into a manhole in the street, and there's, let's say, a spill somewhere. And so there's very little air circulation in this hole in the street. And there's a worker inside that tunnel inside. So it's a confined space, virtually no air circulation. What is that worker's exposure going to be? So if we have such a scenario, then the rule of 10 says we are at 1/10 the saturation vapor pressure, and therefore 1/10 the saturation vapor pressure concentration. If we now go to a situation where there's poor or limited circulation, then we get to 1/100th of saturation. If we now go to, so when I say poor or limited circulation, I'm talking about one or less than one air change per hour. So in that kind of a setting, the expected concentration in that environment is going to be 1/100th of saturation vapor pressure. If we have good ventilation, meaning there is general ventilation and we have roughly 6 air changes per hour, then we are at 1,000th of saturation concentration. So that's the type of setting that you find in many workplaces, many office settings, 5 to 6 air changes per hour. If we are now going even further and talking about capture, so let's say you are transferring benzene from one beaker to another in a lab hood, that is considered a capture setting. And so at that time, the concentration of the worker whose nose is outside of this lab hood would be about 1/10,000th of saturation. And finally, if we have a containment, meaning the worker is not even in operating a hood, but pouring benzene from one beaker to another inside a glove box that is almost completely sealed, then the exposure of this worker outside the glove box is 100,000th of saturation. In this table, we see that as we go down the table, we are getting progressively better and better control of the exposure. And therefore, on the right-hand side, we see that the concentration, as an initial guess, is reduced by a factor of 10 in each step as we go up the chain of improved control. So how do we apply this rule of 10? We first select an appropriate occupational exposure limit, or OEL. We determine the substance's vapor pressure and saturated vapor concentration. So that second step actually is pretty straightforward, because we know from the chemical property of a substance such as benzene what its vapor pressure and saturated vapor concentration are. The third step, however, requires our input, our professional judgment. So we need to look at the workplace and determine what the observed level of control is. So going back to the table in the previous slide, are we considering a confined space, or do we have good general ventilation, or is it a capture hood or a containment type situation? So that is something we need to observe and note. We then estimate the fraction of the saturated vapor concentration based on the observed level of control, and we then calculate the maximum possible exposure concentration that the worker might encounter. We then compare this concentration to the occupational exposure limit and determine which of the exposure control categories the concentration lies in. So let's do a quick example here. So the first step is to select an appropriate occupational exposure limit. And these could be anything from the OSHA's permissible exposure limit, or PEL, the ACGIH threshold limit value, or in some cases you might be interested in finding or using a short-term exposure limit, or STEL, or maybe an 8-hour time-weighted average, or TWA. The second step is to determine the vapor pressure and saturated vapor concentration. So if we know the vapor pressure of the pure chemical, we can calculate the saturated vapor concentration using this familiar formula. The saturated vapor concentration is equal to the vapor pressure in millimeters of mercury divided by 760 times a million, and it'll have units of parts per million. Then we say use our professional judgment and identify the observed level of control. And so let's say that in a particular scenario, we have good general ventilation. And that means, going back to the rule of 10 table, the expected concentration is going to be 1/1000th of saturation concentration. And therefore, we can calculate the maximum expected concentration as the saturated vapor concentration divided by 1,000. And we can use this to estimate where the 95th percentile lies relative to the occupational exposure limit. And so we can find the ratio of the maximum expected concentration to the occupational exposure limit, and find out if this X95 that we calculated is in one of these categories. Category 1, less than 10% of the OEL, 10 to 50% of the OEL, 50 to 100% of the OEL, or greater than the OEL. And that will determine our exposure control category. So let me use a hypothetical case study where we are interested in acetic acid, which is a volatile compound. And it has an ACGIH threshold limit value of 10 parts per million time-weighted average. Then we calculate its vapor pressure, and we can use a lookup table, or actually it is coded into your Excel spreadsheet tool. So the pure acetic acid vapor pressure is 11.25 millimeters of mercury. And if we divide by 760 and multiply by 10 to the power 6, we get the saturated vapor concentration as 14,800 parts per million. Then we go ahead and identify the observed level of control, and we see that in our particular workplace, there is good general ventilation, so roughly 5 to 6 air changes per hour. So we can expect that for this observed level of control, the expected air concentration is 1/1000th of the saturation vapor concentration. So in our particular case, for acetic acid, the maximum expected concentration is 14,800 divided by 1,000, or 14.8 parts per million. And the exposure limit for acetic acid is 10 parts per million. And so our 95th percentile exceeds that, or is 148% of the exposure limit. And therefore, we can easily identify the exposure control category as category 4, where the 95th percentile exceeds the occupational exposure limit. And once we've identified the exposure control category as category 4, we then take the appropriate actions for that category.